MIT aeroengineers are creating a 1 megawatt electrical motor that is a stepping stone toward electrifying commercial airliners. Aviation's huge carbon footprint could shrink significantly with electrification. To date, however, only small all-electric planes have gotten off the ground. Their electric motors generate hundreds of kilowatts of power. To electrify larger, heavier jets such as commercial airliners, megawatt-scale motors are required. These would be propelled by hybrid or turboelectric propulsion systems where an electrical machine is coupled with a gas turbine aero engine. To meet this need, a team of MIT engineers is now creating a 1 megawatt motor that could be a key stepping stone toward electrifying larger aircraft. The team has designed and tested the major components of the motor and shown through detailed computations that the coupled components can work as a whole to generate 1 megawatt of power at a weight and size competitive with current small aero engines. For all electric applications, the team envisions the motor could be powered with a source of electricity such as a battery or a fuel cell. The motor could then turn the electrical energy into mechanical work to power a plane's propellers. The electrical machine could also be powered with a traditional turbofan jet engine to run as a hybrid propulsion system, providing electric propulsion during certain phases of a flight. To prevent the worst impacts from human-induced climate change, scientists have determined that global emissions of carbon dioxide must reach net zero by 2050. Meeting this target for aviation will require step-change achievements in the design of unconventional aircraft, smart and flexible fuel systems, advanced materials, and safe and efficient electrified propulsion. Multiple aerospace companies are focused on electrified propulsion and the design of megawatt-scale electric machines that are powerful and light enough to propel passenger aircraft. There is no silver bullet to make this happen. This is hard engineering in terms of co-optimizing individual components and making them compatible with each other while maximizing overall performance. To do this means we have to push the boundaries in materials, manufacturing, thermal management, structures and rotor dynamics, and power electronics. Broadly speaking, an electric motor uses electromagnetic force to generate motion. Electric motors, such as those that power the fan in your laptop, use electrical energy from a battery or a power supply to generate a magnetic field, typically through copper coils. In response, a magnet set near the coils then spins in the direction of the generated field and can then drive a fan or propeller. Electric machines have been around for over 150 years, with the understanding that the bigger the appliance or vehicle, the larger the copper coils and the magnetic rotor, making the machine heavier. The more power the electrical machine generates, the more heat it produces, which requires additional elements to keep the components cool, all of which can take up space and add significant weight to the system, making it challenging for airplane applications. As designed, the MIT electric motor and power electronics are each about the size of a checked suitcase weighing less than an adult passenger. The motor's main components are a high-speed rotor lined with an array of magnets with varying orientation of polarity, a compact low-loss stator that fits inside the rotor and contains an intricate array of copper windings, an advanced heat exchanger that keeps the components cool while transmitting the torque of the machine, and a distributed power electronics system made from 30 custom-built circuit boards that precisely change the currents running through each of the stator's copper windings at high frequency. The researcher says that they did a very extensive design space exploration where all considerations from thermal management to rotor dynamics to power electronics and electrical machine architecture were assessed in an integrated way to find out what is the best possible combination to get the record specific power at 1 megawatt. As a whole system, The motor is designed such that the distributed circuit boards are close coupled with the electrical machine to minimize transmission loss and to allow effective air cooling through the integrated heat exchanger. To mitigate risk, the team has built and tested each of the major components individually and shown that they can operate as designed and at conditions exceeding normal operational demands. The researchers plan to assemble the first fully working electric motor and start testing it in the fall. Once the MIT team can demonstrate the electric motor as a whole, they say the design could power regional aircraft and could also be a companion to conventional jet engines to enable hybrid electric propulsion systems. The team also envisioned that multiple 1 megawatt motors could power multiple fans distributed along the wing on future aircraft configurations. Looking ahead, the foundations of the 1 megawatt electrical machine design could potentially be scaled up to multi-megawatt motors to power larger passenger planes.